Okay, so now we're recording the lecture. Okie dokie. This is where we finished off, and I'm actually going to go back and just blitz through all this stuff again, right? So we've got, wait, am I sharing my screen? Yes, I am. So we have our linked queue. Okay, great. Int count, front, rear. We like access to the rear to make insertions a lot quicker. I've got my constructor, a copy constructor, deconstructor, and then I have my dequeue, enqueue, first size is empty. Stuff we would typically want. So what's the constructor? Well, start count at 0 and have front be null pointer. Rear, null pointer. Copy constructor, we'll get back to that. Enqueue, pardon me as I look to my other computer over here as I'm trying to run something important. All right, well, that's weird. All right, well, I'll have to fix that one later. So we've got our enqueue, the thing that we're going to enqueue. We create a node of type T. Remember, generic, a new node of type T. We put the element in it. If it's empty, set the front to node. Otherwise, rear is set to next. Rear's next is the new node, and then update what rear is. And then increase count, easy. Dequeue, if it's empty, return the exception. Otherwise, get access to the thing we want to delete. Get the data out of it. Set the front to be the next thing now because we don't want the front to be the thing that we're removing. Decrease count. If it's empty, we need to update rear. Otherwise, delete to delete. Return result. Done. First, it's the same thing, just we don't need to actually delete anything. Size and is empty. Well, here's the size and is empty. Easy peasy. Copy constructor, well, we're just hijacking the enqueue and just taking the data from the other queue and then enqueuing it into ourselves, which is pretty cool. And then the deconstructor, we'll just call dequeue because we know that that deletes everything. There, great. So what does the CPP file look like? Well, it's basically just gonna have the import, right? Okay, so what I'm gonna do is take this code right here and I'm gonna put it, oh my goodness, why didn't I open this up earlier? And I'm just gonna put it in the same file where the main is. I'm not putting this inside the queue. I'm just putting it inside where the main is. And this is just gonna be for easy printing out the contents of the queue. So in hello world CPP, I can just go and delete all this stuff because this is for the stack. Great. Okay, so I'll do that. I guess we're gonna want to include linked queue, QRS, okay. Linked queue, there we go, awesome. Okay, so we've just got this. It's just gonna print out whatever T is. This is assuming that we can print out whatever T is, but we're gonna use simple types, so we'll be good. And with this function, we'll be able to see what's in the queue. All right, so let's go back. So we've got our print queue, now time for testing. Well, let's take all this and paste it here. So what are we doing? Well, we're creating a pointer to a queue, a new linked queue, and we're gonna put ints in it. We're gonna test in queue by adding, I guess, 5 things, and then we're gonna print out the queue. And then we should see 10, 11, 12, 13, 14. Get the size, should be 5, is empty, should be false or 0. So if we run this, let's make sure we're not crazy. So I'm building it. Uh-oh. Exception is not, yes it is. All right, well, whatever. I will just comment that out for now, just to make it. Did I spell it wrong or something? I don't know. What if I do this? All right, well, it's unhappy about something for some reason, so I'll just comment these out. And I won't be able to test the exception bits. but that's okay. Okay, and now running it. Perfect. 10, 11, 12, 13, 14, size is phi, is empty, 0. Good. Okay, let's go back. So the next thing we're going to do is test first. Whoa. Remember, first is kind of like peak, right? So this is just tell me what's in the front, but leave it alone. So we'll get the first, print it out, then print the Q, make sure the first is still in there, make sure the size is the same and everything is as it should be. So first we print out the 10, and then we have 10, 11, 12, 13, 14, 5, 0. Good, 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 good. Test copy, all right, well. I'm gonna create a copy based on Q, print it out, get the size, ask if it's empty, and then I'll immediately delete it because all I'm doing is just doing this to test if the copy works. So let's see. Looks good to me. And test DQ, and then more test DQ. One, two, three, four. Ah, okay. So first what we do is we're DQing one thing, printing out the Q to make sure that it's gone, and then get the size and get is empty. This will look like it hasn't been DQ'd, but you got to remember we're DQing the 10, printing it out, and then immediately we're printing out the Q, which will then return 11, 12, 13. So maybe I should do something like this to make it a little more obvious that there's a gap. And then more DQ, I'm just DQing the rest of the things. This should be 0 and 1 for true. I think that's all I'm really going to test here because the extra first and DQ won't work because I've got the exceptions in there. But yeah, look at this. 10, 11, 12, 13, 14, 4, 0. And then we print out all the stuff and then it's 0, 1, 1 for true. It's empty. And yeah, here's me trying to catch the exceptions, but for whatever reason, I don't know, it's not working. Priority queue. So, and this is going to be important. Whoop. This is going to be important for your assignment 3. A queue is a very high level idea, and then we can have very specific implementations of a queue. We can decide, well, I want to have a very special queue. For example, a priority queue. And priority queues are fantastic, and there's a number of ways to implement them, but a very easy way is to implement them as like a queue, like maybe a linked structure or maybe an array structure. And we will talk about implementing an array queue in a moment. But the priority queue is going to be relevant because of assignment 3. So whenever we in-queue something in a priority queue, we're going to in-queue it, but it goes in based on a priority. And then when we dequeue, we remove the thing from the queue with the next highest or lowest priority. So the idea here, let me open up Paint. The idea here is something like triage. Okay, when you go to the hospital and you've cut your thumb and you need stitches, you know, you were there first. And a typical queue is first come, first serve. But if you go to the hospital, the emergency room, and your nose is, or your thumb is cut, and someone comes in and they've been shot, I don't know, from all the bad shootings we have in Antigonish, someone goes in and they get shot, well, they're going to jump the line, right? Because they're going to come in with a higher priority. So the priority queue is that idea. It's whenever the rule is we add things to the queue, and then when we take something out of the queue, the thing that comes out should be the one with the most pressing priority. Sometimes we want our priorities to be like bigger number means more priority. Sometimes we want smaller number means more priority. So that's just a switch from less than greater than type thing. But I mean, there are two ways we can implement this idea. So all that really matters is when I dequeue something, the thing with the next lowest priority comes out, or highest priority. let's say I'm doing a minimization problem. So I want lower priorities. Lower priority is better. I've got two big options here. How should I go about implementing this? If I have my queue, I'm just going to draw it kind of like this. Okay. If I have, I guess I'll just draw these as numbers like 1, 7, 2, 0, 4. Okay. This could be my queue. And every time, like if I'm going to come up with a new thing that needs to be added, let's say I add another 0 or something, I'm just going to throw it into the back of the queue. But when it comes to the D queue, I can't simply just take from the front anymore. Where's my little cursor? Hello. All right. I can't just take from the front because the 1 isn't the lowest. We've got a 0 here and a 0 here. So I can't just take from the front. So what am I going to have to do? Well, I'm going to have to do a linear search. I'm going to have to do a linear search to look for the smallest thing. 1. Okay, that's the smallest I've seen so far. 7, 2, 0. Ah, okay, so now this is the smallest I've seen so far. 4, 0. Oh, well, we already have a 0, so I guess it'll have some amount of first come, first serve. So everyone with the same priority, well, it's first come, first serve for that. So in this case, when I do a DQ, I'm going to have to do a linear search. But when I do an in queue, it's easy. I just throw it onto the back. So let me ask you, with this strategy, what is the computational complexity of our in queue? And remember, let's think about the linked structure here. We have a pointer to the beginning and a pointer at the end. So what's the computational complexity here for our in queue? If we implement it this way, what do we see? Whoop, not that way. Where the heck? Ah, 1. And no, it's 1. It's going to be 1. Why? Well, because all we have to do is create a new node, have the last point to the new node, and then make last point to the new node. Wait, let me say that again just to make sure that wasn't confusing. Make a new node, have last's next be that new node, and then set last to point to the new node. So that's order 1, because it's just a couple of steps. The amount of time and work we got to do does not depend on how many things are in this queue. So our in queue, I guess I should have this. Our in queue will be order 1, but then what is our D queue? That'll be order what? What do we think? N. Absolutely. Because we're going to have to do that linear search. We're going to have to go through, because the only way I'm guaranteed to find the thing with the lowest value is to look at all the things, all N of them. So in this scenario, it's that. However, we can have an alternative setup. I can show up and implement this a very different way. Let me just make this bigger. So the other idea is when I have my queue, I will insert things such that they're going to go in the sorted order. So if I have the number 3 here, and then I want to come in and insert a 1, well, I'm going to have to put the 1 here and then move the 3 back, right? And then if I show up and add a 4, okay, well, that's easy. I just throw the, let's make it a 7, actually. I just throw the 7 there. But then I show up and I need to add a 2. Well, all right, well, I got to go back. 1, 2, 3, 7. And then I need to go, and maybe I'm going to add a 6 this time. All right, well, let's do 6, 7. So every time I do the in queue, I have to make sure I'm inserting that thing in the proper location. But now the DQs are really easy, right? Because the DQs are just, well, if the thing is sorted, and I'm looking for the things with the smallest priority, if the thing's sorted, well, DQ is just remove the first thing. That's it. So in this case, DQ is order what? Well, that should be 1. But the in queue is the one now that looks like it's going to be a little bit more work. What do we think? Well, I mean, in order to know, if I have this thing of some arbitrary value coming in, x, if I need to know where x goes, I'm going to have to look at this whole thing to determine where it goes. I mean, maybe I get lucky, you know, because if I have like a 4, well, I don't need to go to the end. But for all I know, x is 99. So maybe half the time I get lucky and the numbers are this half. So I don't actually have to do a linear search that far down this line. But a lot of other times I'm also going to get very unlucky and they're going to be on this half. So on average, it's going to be like the length of the search I'm going to have to do is going to be like n over 2, which we can write as 1/2 n. And then do we care about this 1/2? No. So this is going to be order n now. So InQ in this scenario is a little worse. Which implementation is better? Well, that's entirely up to you. The implementation, maybe the way you're using it is, you know, I know that I'm going to be probably InQing a lot of things and I'm never going to really DQ a lot. I'm going to InQ all these things, and at the end of the day, really the number of DQs I'm going to run is much smaller than the number of InQs. Well, if that's the case, I'm probably going to want to use this scenario because, okay, DQs, sure, they're slower, but I'm going to do way fewer of them. And if the thing I'm going to do more of, like InQ, well, I'm going to want that implementation. And you know, if you really think about it, is it possible really to ever do a DQ more often than an InQ? No, right? I mean, you can DQ, but I mean, then it's just going to throw the exception. So at the end of the day, maybe this one's better if we're only going to DQ, because at most, the number of DQs will be equal to the number of InQs. Minus the fact that, you know, the exceptions. Because the number of DQs, like, we can't DQ things out of the queue if there's nothing in there. And we only get things in there if we InQ. But anyways, any questions about that, about priority queues? Because they're going to be important for assignment 3. So now's the time to ask. And but before I get any questions, that I will answer one question that I'm probably going to get. Am I going to teach you how to implement it? No, I'm not. A big part of the exercise of assignment 3 is like, okay, it's still maze solving, but now you need to use a different data structure. And what data structure? Well, I can't make it as easy as copy and pasting the queues, right? So I got to give you a bit of a challenge. So the challenge is implement a priority queue. But at the end of the day, it's just going to be like inserting or deleting from the center of some structure. Some like collection of things. So maybe the array, maybe the link structure, right? So you'll have to do a little digging on implementing, but I mean, I gave you all the ideas there. The ideas are, you know, the InQ, DQ, which implementation should you use? Well, I mean, that's up to you. At the end of the day, all I really care about is I put things into the queue, and when I take things out of the queue, the thing that comes out should be the thing with the next most important priority. I heard a boop. Can we just use the first one and not use complex conditions we would need to insert in order for the second one? I'm not sure what you mean. Can we just use the first one and not use we need to insert? Yeah, but then you're going to have to do the complicated delete, right? Because you'll have to do the linear search and then remove the thing from the queue from potentially the middle. So the complexity comes on, well, there's no free lunch in this scenario. Could you use a binary search instead of a linear search? So yes, you totally could. In fact, later when we implement, if we have the time in the class this year, like Cole, you're absolutely correct. But we'll actually have a better way of doing your idea, because when we start implementing trees, we'll talk about binary search trees, which are awesome. And no, we absolutely will have time to do that. And a binary search tree can be used as a priority queue really easily. And so it ends up being much, much better because then your DQs can be way, way faster. Anyways, can we make nodes with 2 data slots? You could, but why? I mean, there's no rule saying you can't. But in general, I mean, my answer is why. One for oh, of course you can. Of course you can. Yes. So I mean, see, that's not really a data slot, right? It's just another attribute that's holding on to the priority. But yes, you absolutely could do that. In fact, I would recommend. I think in the assignment I say build a priority node, and I tell you to do just that. Other questions? This is good. I like the questions coming in. All right. Well, if I hear another boop, I will come on over. But now, let me just go open up the slides. Don't need this anymore. Delete, close. Okay. Yes. So now we're going to do array queues. So another queue. The same thing though. We're going to have our in queue, our DQ, size is empty, first. But instead of with the link structure, we're going to have our array. Okie dokie. No. What is it? There we go. Okay. So an array queue. Well, we're going to talk about a few ways we can go about implementing a queue with an array. We're going to look at good ideas and bad ideas. All of them are workable, but some of them are trash. And then we're going to implement a queue with an array. So the queue implementation issues. We need a container, an array. Great. We need something to keep track of the front. Well, I mean, that's easy. Like an index, maybe it's 0, We need something to keep track of the end. Yeah, okay, like kind of like top, right? So just have another index. So it's like an integer that just represents the index in the array. And we need to keep track of the size. Okay, cool. Another integer. I mean, heck, we can even do something like take the end minus the start, whatever. But we can just keep track of it as an integer. Great. So here's an idea. Here's how we can go about implementing this queue. We will always have the front be index 0. And have the index keep track of the rear. So if I show up and I have like a couple things in here, maybe I've got like A, B, C. Maybe I can have like rear B3 in this case, so it's kind of like this. Kind of like top was, right? And this will also tell us what the size is, which is handy. So this will work. And then whenever I need to DQ, so whenever I in-queue, this is easy. I just go, okay, D, and then move this to 4. There, easy. In queues, trivial. Order 1, right? We just add it. But then we have about a bit of an issue. Oh, look at that. Will this implementation work? Is it correct? Absolutely. Will we ever have to expand capacity? Yeah, probably, right? What is the computational complexity of in-queue? Well, it was order 1. And what's the computational complexity of DQ? If I want this to be such that index 0 is always the front. If I ever want to remove the A, right, what do I have to do? Well, I'm going to have to move B down. Then I'm going to have to move C down. Whoop. D down. And so on and so on and so on. What if I have like a billion things in this queue? Whoop. How many things am I going to have to move down? Like a billion. So in this case, the in queue was easy. It was order 1, right? We just threw it in at the end and updated the rear. But the DQ is pretty hairy. The DQ is order n, because we're going to have to shift everything down if we want to ensure that our index 0 is the beginning. And I suppose I should say like this is an amortized order 1 because we might have to expand capacity, right? But really it's going to be like order 1 and the DQ is order n because we're going to have to shift everything, which is garbage. That's really bad, especially when you consider the fact that with with the linked queue, not the linked priority queue or any priority queue, but with the linked queue, the in queue was order 1 and the D queue was order 1. In queue, just add a node to the rear. D queue, remove a node from the front. Those are both order 1 operations, and the amount of work that they have to do does not depend on the number of things in the queue. But here, now our D queue is order n. And at this stage, if this was our implementation, I could code this. If I code this, it'll totally work. But this would be a horrible idea because this linear time, that's garbage. That's garbage when your alternative is order 1. So we would never want to do this. So let's try another idea. What if have an index keep track of the front, have an index keep track of the rear, and then we do something like this, where, okay, front, there, we add something perfect, then we remove it, and we update the front to be 1, right? So let's go back to this. So if I have like A, B, oh my gosh, I hate this so much. C, D, I do not know why my computer does this. It does it with my mouse, it does it with this fancy little pen thing. Weird. So this will be, like front in this case, will be 0 and rear will be 4. If I want to show up and add something, okay, great. I put that and then that becomes 5. If I want to dequeue something, okay, great. This becomes 1. Fantastic. But can we see any downsides of this? Because here, like, look, will we have to do expand capacity? Yes. What's the computational complexity of in-queue? Well, it's order 1. I mean, might be amortized because we might have to do expand capacity because our array runs out of space. But what is the computational complexity of dequeue? Well, in this scenario, it's order 1. Right? We just remove it. And we don't have to do the shuffling, which is fantastic. We don't need to worry about doing this. The shuffling down to make sure front's always 0, not an issue anymore. This is not a thing. So suddenly, we've got a way better implementation in terms of computational complexity. Both in-queue and dequeue are order 1. But can you see any potential issue with this? Well, that's a spoiler. Can we see any potential issue? Whoop, nope, I keep going the wrong way. Is index 0 still, I mean, yeah, so index 0, the array is still there. The place in RAM that corresponds to index 0 is still allocated, but we can never use it anymore. It's kind of like a memory leak, kind of, because it's there, but we can never have access to it. So when you think about it, if we go here and I ask the question, how often are we going to have to call expand capacity here relative to idea 1? Well, I mean, it's going to be hard to put a hard number on that. But if I have, like, if I keep shuffling things down, I will free up the space at the far end of my array, right? If I keep shuffling things down. But if I don't, I'm never going to free up space every time I do a dequeue. Meaning, this has the potential to grow way faster because we'll end up having wasted space in the front. And in the end, we're probably going to end up having to call expand capacity a lot more often compared to idea 1. So now we have another trade-off. You know, there's no free lunch in this scenario. You know, we're stuck. However, well, okay, which would you prefer? Can we think of another implementation? All right. So now it's quiz time. Now, maybe some of you have looked ahead, and if you have, don't spoil the fun for everybody. But now, can we think of a better implementation? I'm looking if we have any ideas here. And if we were in person, and if it wasn't COVID and, you know, we could interact, I would typically, in this case, I would usually bring students down and we would do a bit of a demonstration to show how it works. But I'm curious, does anyone have any idea? I'll give you a couple more seconds to see if anyone squeezes out of their noodle. So it looks like we're out of it. Oh, just make the highest index the front of the array and add things to the lowest index? Well, no, because then whenever I mean, that could be like another idea, but that in that case, whenever we in-queue, we're going to have to shuffle everything down the other way because we need to make room at index 0. So that, I mean, there's an idea, and that is a totally workable solution. But the in-queue would now be order n because we would be guaranteed to shuffle down, plus, you know, maybe some expand capacities. All right, so I'm going to see, maybe I'll do it this way, paint. All right, so let's say, we're playing, I don't know, musical chairs. Okay, I'm going to draw a bunch of like seats. Assume these are chairs. We're not actually going to play musical chairs, but imagine this. I have 1, 2, 3, 4, 5, 6, 7, 8 chairs. There's 8 chairs. Right? And I don't know. What I'm going to do is I'm going to have students start sitting down in these chairs. So maybe, I don't know, I'll have student A sit here. And then I'll have student B sit here. And every time I tell a new student to sit, they'll just go in the next seat clockwise. So C. And then maybe I tell D to show up. But then maybe, I don't know, I tell A, look, you can stand up. We don't need you anymore. You can go. Maybe I tell B, great. Tell C, okay. But D, you have to stay there. Maybe I'll have like E now. E will sit here. We're always going clockwise. F, G, H, I, J, and now I'll do a couple of telling students to stand up. That's going to ruin part of my chair, but that's okay. There. K, L, M. Nope, no. G stands up for whatever reason. And, oh, uh-oh. You know what? It looks like we're at a chairs now. There's too many people. We have 8 people sitting down in the 8 chairs. So you know what? Maybe we'll expand capacity. Pardon me. We'll double the number of chairs available so we have 16. And we'll keep doing this. Does this idea make you think of anything? Let's see. Based on that little musical chairs style example thing that I did, does it give you any ideas on how we could think about implementing our queue with an array? A matrix. No. I'm not sure what you mean, but the answer is no. That's not where we're going. Shot in the dark. Okay, yeah, well, it was a good try, I suppose. Let me go back to my example here. So I'm going to, and I'm going to keep having you thinking about this because I think this is a much more important, like this is an important idea to kind of discover for yourself. I don't want to just tell you the answer. Let's clear these out. All right, so we have 8 chairs. We go that way. All right, I heard a boop. What do we got? Use an attribute as next value to fill that overflows once it hits the end. I think what you're saying is what I'm going for, but I'll draw this idea again. So how about this? You know what? I'm gonna have an index for all these chairs. Each of these chairs is gonna correspond to a number. So we have 0, 1, 2, 3, 4, 5, 6, 7. And when I have, and you know what, I'm also going to keep track of like the front and the rear. And in this case, there's no one in my queue. I mean, pardon me, there's no one sitting in my series of chairs. So I'm going to pick a different color here, purple. Front is equal to 0 currently, and rear is equal to 0. Okay, great. So now let's come along and A gets added. So now when A gets added, well, we update front to be, or pardon me, rear. It's now 1. So let's add a new one. B. Well, now this is now 2. C. All right, well now rear's 3. Maybe let's do a DQ now, right? So now we'll go. All right, so now the new front, the next person to be removed should be from seat 1. And then maybe we do C, D. I'm just going to do a bunch. E, F, G, H. So now rear is 7. Oh, wait, no, it's not. What should rear become now? I think based on what we just saw from Alex was, well, maybe rear should be 0. In fact, I heard a boop. What do we see? What do we see? What do we see? 8. Never mind. Well, there is no 8. So in this case, it would be 0. Because we ran out of space. So what comes after 7? Well, I mean, when looking at this like the clock, well, we go back to 0. So rear is now 0. So if we show up and we want to add something, maybe we add I. Well, now rear is now 1. Now we're in a bit of a sticky situation because when rear is 1, well, now we know we're going to need to like expand capacity, right? Because, well, we're out of space. But here's the idea. We can just, whenever we run out of room, it's basically idea 2, but whenever we run out of room at the end, we'll just loop back to the beginning. Isn't that a great idea? This is magical. What a wonderful idea, right? So, are there any questions about that idea? I'll give you a second to think about it. Hopefully that noise in the background is not too annoying. All right, so here's the idea. We're going to have a circular array. Now, in reality, the array is going to be, it's still linear, but we can pretend that it loops back on ourselves. So for example, we pretend we have an array of capacity n. The index that comes after n, comes before n is n minus 1, and the index that comes after n is 0. So the index that comes before 0 is n, the index that comes after 0 is 1, and so on. So this is the idea. We'll keep track of the front and the rear. And I mean, this is just showing you what I already did, except I guess with 12 seats instead of 8. So what we can do is we can have like our queue. We can keep track of the front. We can keep track of the rear. We can keep track of the count, or we could just do the difference, I guess. Although that might be difficult when rear becomes smaller. So maybe we can't. Maybe we do need the count. And we'll have queue, which is just a pointer to an array that we're pretending loops back on itself. Rear is 2, front is 98, yeah. So like this scenario can happen. The queue only has 4 things in it, and it's from here to here. This is the front, this is the rear. Or really this is rear, because this is where we would add next. So this is the same idea here. It's just, obviously the array does not loop back on itself, but we can do fancy math here to make, well, what comes after 99? 0. We can do that. So it's going to be complicated to keep track of all this bookkeeping, but it's actually really easy if you know one simple trick. And some of you may already be familiar with this simple trick, but here it is, percent or mod. Who here's used the modulo operator before? Put up your hand, I know you have. So what does it do? So all it does is basically it tells you, like, do division, but tell me what the remainder is. So yeah, remainder, basically. So if I said, I don't know, 1 mod 2, well, that's equal to, well, how many times does 1 go into 2? 0. What's left over? Well, 1. What's 2 mod 2? Well, how many times does 2 go into 2? Once. What's remainder? 0. So imagine I had like 99. No, let's do 98 mod 99. So how many times is 98 going to 99? Well, 0 times, but what's the remainder? 1. If we do 99 mod 99, well, oh, that goes in 0. So we can do a check to see, well, if we ever do something and we add 1 and it becomes, you know what, it's going to be easier if I just show you. Yeah, yeah, I already did that. It's really handy for figuring out something is evenly, yeah, okay, we've already done that, yeah. Okay, great. Okay, here's the fancy math. Rear is equal to rear plus 1 mod 99. Wait a minute. Why did no one stop me at my horrible, embarrassing error? 98 mod 99 is not 1. What is it? 98. Geesh, we need to start, just like last time, we need to start getting rid of letters in the alphabet. We need to start getting rid of math. I don't know. All right. So what we'll do is rear is equal to rear plus 1 mod capacity. So if we had, let's say capacity was 10 for simplicity. If rear was 7, well, 7 plus 1 mod 10. Well, that's 8 mod 10. That equals 8. Okay, so now it's 8. 8 plus 1 is 9 mod 10. That's great, 9. So it just goes down. So whenever we add 1, the next index just increments by 1. But once we hit 9 and we add 1, it becomes 10. Well, what's 10 mod 10? Well, that equals 0, which is fantastic because we have an array. I mean, we have an array of size 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But that's indices 0 through 9, right? So what index should come after the 9th one when we do 9 plus 1? Well, it should be 10, but that just goes back to 0. Huzzah. Fantastic. Isn't that lovely? Just gotta keep track of the time here. Okay, we're running low, but we're doing okay. So yeah. So we need the special expression for updating the rear. Do we need it for the front too? Yeah. Can the idea ever run out of room in the array? Yes, we can. We still are going to have expand capacity scenarios because it's possible that, well, you know, there's only 8 seats and we want to add that 9th person. We're going to need a bigger array to treat as a circle. So yeah. Suppose we try to add one more item to this queue. Great. So now it's full. How can you tell? Well, when they're the same. If I want to add a new thing, how am I going to do this? Right? Because if I just double the size of the array, remember, this is the front and this is the rear. But again, rear is going to be 2 because it's the index of the next available spot. But of course, we're out of room. So the blue thing should be like first, second, third, fourth thing out of this queue. And if we just double the size like we did here and copy everything over, we're in trouble because we now have 1, 2, I don't know what's going on over here. We've got a whole lot of nothing. And then we've got 3, 4. Like we've suddenly inserted a giant gap in our queue, which is a big problem. So we can't just double the size of the array and copy everything over. We're going to need to have some fancy way of moving things over. And what we could do is just basically say, okay, start at the front, copy over, but then when we would loop around, well, we can just start adding things to the end again, right? Like we can keep going. Or what we can do is just the same idea, but you know what? Instead, we'll just put the front back at index 0. Is this truly better than this idea? Not really, I guess, but it's just perhaps a little easier for bookkeeping. So, will this implementation work? Yes, it absolutely will. What is the complexity of InQ? Well, it's order 1 plus potential expand capacities. And DQ, order 1. How often will we need to call expand capacity relative to idea 1 and 2? Well, I guess it'll be as often as idea 1, but our DQ is way better than idea 1. It's constant time, not linear. So now we could talk about the implementation, but we won't do that today because we're basically out of time. Okay, are there any questions before we wrap up for today? Yeah, what's up?
If we move the pointer back to the start when we expand capacity, doesn't that change where the start is of the queue, or like what should be DQ'd next?
Well, when we expand capacity and we copy things over, we will have to also update front to be 0 again. Does that answer your question?
Not sure.
All right, well, you know what?
Sure.
Once we get to the implementation that we'll talk about tomorrow, hopefully it fills in the gaps a little bit more. But good question nonetheless. It's the question you're bringing up is just is pointing out the fact that we got to be careful with our bookkeeping here, because if we're not, we can end up in big trouble. And the bookkeeping is more complicated, but it's not complicated. Hopefully we'll get this. We'll have an appreciation for that once we look at the implementation tomorrow. Any other questions? All right, in that case, I'll see you all tomorrow. Try to enjoy the rest of your day.